could share it, to the presentation mode after you introduce. Will that be okay?
Yep.
Okay.
Okay. Good evening, everyone. My name is Stalin Paucar. I am the president of the SEG student chapter at the Central University of Ecuador. It is a pleasure to welcome you all to this lecture. It is also an honor to welcome Dr. Abani Samal, a mining industry expert with a PhD from Southern Illinois University, Carbondale. He has a diploma and a Master of Science from the Imperial College of London and a Master of Technology in Mineral Exploration from India Institute of Technology. He is the principal of GeoGlobal LLC, providing consulting services worldwide in mineral deposit evaluation, applied geostatistics, and mine mill reconciliation. He is also a fellow of SEG and SME. Dr. Samal is also involved in professional organizations such as the Canadian Institute of Mining, Metallurgy and Petroleum, the Southern African Institute of Mining and Metallurgy, and the Prospectors and Developers Association of Canada. He serves on the editorial boards of Mining, Metallurgy and Exploration, Natural Resources Research, and Mining Engineering Journal. We are pleased to have you, Dr. Samal, with us today to share your expertise. To the attendees, if you have any questions during the presentation, please leave them in the chat and we will address them at the end. In Spanish, I will say only something. Un saludo especial a Frailin Esteves, de República Dominicana, y a Miguel Gutiérrez, de Chile, por su colaboración y aporte a nuestro capítulo. Without further ado, we can start. Dr. Samal, please.
Thank you, Stalin. Can you see my screen now?
Yeah, we can see your screen.
Okay. So my name is Dr. Abani Samal. Like Stalin said, I have education in the United States, UK, and master programs in India. And I have been in the industry since 1996 January. And I've worked on various commodities like gold, silver, copper, iron, titanium, uranium, thorium, and all different kind of things. But you will see that I am not an expert in coal deposits. Okay, so and in this particular slide, you see the first line in here. It says that I am a CP or QP, that is a qualified person. That means when I can sign or I can certify a company's mineral resources. And in this presentation also you will see towards the end what that means. These are the countries where my projects have been located, but I have not been to all countries. Like I have not been to Australia, for an example. I've not been to Papua New Guinea, or but I have been to about 17 countries working on various projects. Today, we're going to talk about resource modeling. You'll see that, I'll start with very basics of it and try to see why it's important in the mine value chain. To understand that, let's talk about what are projects. In mining industry, project may mean doing some work during all these type of different stages of the project, like preliminary exploration and advanced exploration, project construction, mining. So I have simplified this. This is called mining value chain for a project. Start from the exploration to construction to mining, but this is not the whole picture though. Of mining, I mean the mineral extraction. After we extract the minerals, we go to process it and sell it, right? And then when mine closes, you have to close the mine with the required setups that you have done. And the mining project has agreed with the government. That's not what we're going to focus toward the end. That's not what we're going to talk about in this presentation. So I'm going to focus from exploration to mining. In these, what you see in the second line here, when we talk about a deposit, at the preliminary exploration, we're talking about mineralization. but not able to say mineral deposit. They're two different technical terms. Mineral deposit happens when you have an advanced exploration. That means you know more. And in all these, you actually do actually resources, mineral resources. That means we quantify the amount of the rocks in there and what amount of metals that can be extracted from a deposit. And also there's another term called mineral reserve. Remember, reserve is basically mineable resources, okay? Reserve is always, I underline the word always, a proportion of or a subset of mineral resources. And it always goes from left to right, like it shows in the slide. In the Canadian term, these are the arrows that you see in the various studies. We do conceptual, or PEA means preliminary economic assessment. In the United States regulation, they call it initial assessment. The meaning is very similar, not exactly the same. I'm guessing that you have heard about PFS, or pre-feasibility study, and then moving on to feasibility study. Why we do all that? The last two arrows are very, very important in this particular slide. As you go from left to right, this yellow arrow says, well, you change the definition. And with increased of confidence, that means when we say in the beginning, we said actually it's a mineralization going to deposit, that means we know a little more about the mineralization. When you say resources, that means we know much more information, not really quantity-wise. We have more detailed information. We can quantify how much commodity is there. When it's a reserve, that's why I'm saying, well, out of all the commodities, we can mine this much. So that yellow arrow means that. And the blue arrow really means, the last arrow in this slide means when you go from left to right, we decrease the confidence. Decrease the risk and increase the confidence. In all these cases, we have resource reserve estimation. Every stage and every study that we do, we have this exercise done. Remember the one word here, we are saying estimation. We're not saying calculation. It's an estimation, okay? Like, I touched on this. Let's focus on on the last 3 points in this slide. These are studies designed to evaluate the potential viability of the resources. What that means, when you start doing a scoping study, a preliminary economic assessment by, like it said, it's designated in Canada. When you do that study, we have still certain things we don't understand as much as we could during the PFS. During preliminary feasibility study, a pre-feasibility study, we do a lot of work. That's the most exhaustive study that we do. Feasibility study means at the end of the feasibility study, we define whether the project is feasible or not. This slide has a lot of words. Just focus on the words that are highlighted with underlines or italics or bold, okay? In the beginning, in the first slide, it said, okay, it's mineral occurrences or mineralization. That's basically, we know there's a concentration of minerals. Like you can say, well, the building was sitting actually, below that, there may be some material with gold and, other elements with it. That's just occurrence. That means it does exist. When it's a deposit, that means we can quantify at least vaguely. We can say, well, it is big enough, or it is quality-wise good enough to have economic potential. That's called deposit. Ore deposit means ore comes from reserve. That means it is definitely going to be mineable, provided we construct the mine to mine the material that we are interested. So there's a lot of words in this slide. If you're taking a slide screenshot, please do so. And you will find these deposits, these definitions in different codes. I'll show you where these are. Here the diagram that you are seeing, this is a two-dimensional diagram. There are 6 terms in it. So, here there's one thing is called exploration results, the 3 categories of resources, 2 categories of reserve. The diagram is designed in a way that if you go from top to bottom, you are actually increasing the confidence. And if you're going from left to right, you're also increasing confidence. So for an example, you can actually have exploration result. That means you drill some data, or even if the pre-drilling, you did some collect some samples, you document them. That you can show the shareholders through a stock exchange. Say, well, tell you what, I have a deposit. It has all this data. That's called exploration results. And then when you call resources, there are 3 categories: infer, indicator, and measure. Like I said, this arrow says the increasing level of geological knowledge and confidence for resources. As you go from infer to indicator, indicator resources have more confidence than the inferred resources, and measured has the highest confidence. Okay, as you making resource reserve, what we do actually, we apply this called modifying factor, this kind of filters. Okay, I'll give an example. Let's say you have a deposit with 50% of the deposit actually indicated resources. That 50% resource deposit can potentially become a probable reserve, provided they meet the criteria under modifying factors. Okay, modifying factor means if you can read, it says, well, if you have these resources, can you market it? Are you legally, you can mine it? If environmentally you're doing all the good things, and this material that are mining, and we can process it, and then still actually the project will be economically viable. All those questions answered, then that portion of the indicated resource can become probable reserve. You can see, so the confidence really increases from resource to reserve, going from left to right. Just remember that from this lecture. This is second point, you must remember that. And this diagram is used actually now in 15 different countries. They are called members of CRISCO. CRISCO is an umbrella kind of non-profit, non-government organization. And there are 15 different countries which are members of this. So United States, in the right-hand side table, you see the 4 countries I've highlighted with yellow. These are the founding members of this organization called CRISCO. CRISCO doesn't have a static office. So whichever country becomes the president of CRISCO, for an example, right now, it's Canada is the president of CRISCO. So they're maintaining the office work from Toronto/Vancouver, wherever these gentlemen are. And it's a little more complicated than, what I just said. And in another time, if you are interested, we can discuss about CRISCO. It will take at least a couple of hours to discuss about it. You can see that 15 different countries which are members, and here are where they are located. You can see a lot of African countries that are not members, okay? And in Asia, there is China has not been a member yet. I'm hearing they'll be a member this year. Also in the South America, there are not many members in there. I remember going to Brazil in 2015 when they joined CRISCO. As of today, these are different. There are 6 different countries that are trying to be member of CRISCO. If you go to CRISCO.com, you will see these are candidate members. What you should know that even Saudi Arabia is trying to become a member of CRISCO. The beauty of having that member of CRISCO is they use the same terminology, same definition. So what is resource in let's say in India, as using the Indian code, will be also called resource, and in the United States using United States code. That they are done that way. Now let's get back to the main topic here. So in the mine value chain, like we talked in the beginning, I showed you from exploration to mining, but like I said, there is processing that's, going to metal going to be extracted. The whole mine valuation is there. And in all that, going from step 1 to step 2 to step 3, every time we have a resource estimation done. Now, if you look at the same diagram slightly differently, you'll see that when the mining happens in the beginning of this mining project, just before the mining really starts, we are actually generating a lot of data. We're planning for it. After the mining, there are a lot of commodity is coming, like the mine is producing rocks, goes to processing and grinding, milling, then we're trying to get a concentrate. Then from there, we're going smelter. So left hand of the slide, left hand of the slide is basically says, well, here's all the data that is generated. And then on the right hand side, this shows that in the value chain, there is here is where the commodities show up at different stages. But remember, sometimes we may have a mining operation going on, and then we're also starting to do exploration. That's always the case, right? Or not sorry, it's not always the case. It's most of the time that's the case. So you are having a pit that's being mined, but at the same time you may have a brownfield exploration going on the same project, right? So it can happen like that too. So when you're producing metals in here, you may be also trying to expand the deposit, doing more exploration. However, this is how the data and information flows from left to right. In all these cases, we do resource and reserve estimation. You saw what the position is there. Now, in the resource estimation, what we do at the end of the estimation, we say, well, how much, right? What's the grade? That means what the quality of the commodity that we're going to mine? How much tonnage of the deposits, of the rock that we're going to mine? And to do that, we follow a very stepwise process. For me, there are 6 different steps. The first step is field camping, or let me see, go to another slide. Okay, this one. So first step is data collection or QAQC. It's not just drill hole data. It can be topography data. It can be drill hole location. It can be geological structure that you are mapping. Then geological model is basically interpretation of the data that you collected and put that in a 2-dimensional or 3-dimensional kind of solids there. Okay, then when you have that, we want to just say, well, we have all the data. Now, how we predict the grade and tonnage? There is a process called EDA, exploratory data analysis. That is the statistical analysis, visual inspection, and there are also geostatistical models that we do. I am a geostatistician by training and practice. If you are more interested, you can always take questions and discuss that. Now, you can see the grade estimation where we have generally we call it the block model estimation in here, or the product is a block model. You see that the block model to happen here, we have to have estimation exploratory data analysis done. For all those who are in the beginning of your career attending this program, just remember, and you can quote me on this, more time you spend on exploratory data analysis, more confidence you have in the resource estimation, and you will spend less time correcting your resource model. I strongly suggest you look at the exploratory data analysis, not just statistical tables. It has a lot of things in it. And the grade estimation is basically we optimize the parameters and interpolate the numbers. Then we estimate the grades in a kind of a 3-dimensional space. It's called a block in a model. Classification means we say, well, out of all these blocks, which can be mined, I'm saying can be mined, sometimes in the future when the right techno-economic conditions are correct or favorable, that's resource. Now you can go to next step, which is reserve, but that's not part of this, this discussion here. So I stop at resource classification here. Now, geostatistics are applied in all different steps. People sometimes ask me why would you do actually geological model? Actually, you have a geostatistics application. The answer to that question would be yes. The heavy application of geostatistics happens sometimes linear, sometimes non-linear, to create or validate a geology model. That's always the case. Now, like I think I just mentioned that what we're talking about is grade estimation. We're not saying grade calculation. The reason being the calculation, the results are definitive. So there is a definite answer. For example, 2 times 20, 2 times 13 equal to 26, 2 times 23 equal to 46. There is no debate about it. But estimation really means it's a good approximation. It's a good approximation. It's an approximation. Now, the best estimation is the one that is the grade that we estimated. Like I said, it's an approximation using the mathematical work that is close to reality. Those are the ones, and that's the estimation we call it better estimation, right? Than the other one. If you have done more than one, estimation for a deposit. Here's an example. If you have like say 2 points in here and you have some values there, you can easily say estimation. Okay, we can estimate where this question marks are. The moment I say, well, here is the distance of separation between two samples, which was not given in the first case, you will have a better estimation than the first. Like first, you said a kind of guesswork. Now you can have a better estimation because you have more information there. And the moment I say, well, tell you what, these distances have a relationship too. That means you are using more information in estimating the value. Therefore, what you'll see that more added information is there, you have a better confidence on the grades. So let's spend a little bit time about the data. Data doesn't necessarily mean all the drill hole data. Okay, it starts with the topography, geological mapping, fault, structured maps, drill hole data, and density data, right? And in some projects, you will see they actually do a lot of structural mapping, lithological mapping, and alteration mapping too. This is just to show the types of data that we may need. But every type has many subtypes. Like geological mapping, you can have a rock type mapping, you can have alteration mapping, you can have many different types of mapping there. An example of this topographic data, I showed this example just to discuss that. Make sure that your coordinate system are accurate and they are the same. When your coordinate systems are not the same, even if they're similar, there can be problems. Please avoid it. If you have data coming from many different sources, make sure that coordinate systems are exactly same. When you go to in the field, this is the drill location, the picture I took in 2009, I believe, in Brazil. Then you want to get all the data from with the drill holes. What was drilled, who drilled it, when it was drilled, what are the information, and all the information that you will see that the core boxes involved, people are involved in logging them. This is just an image I downloaded somewhere from internet. It shows that how drill logging, there are some people I met actually, they love drill logging because they're very detailed on what they're seeing on the rock. And that's very, 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 very important. Very, very important. Once you got the data, now you can say, well, let's interpret the geology. Let's interpret the geology and then see what the grade model looks like. On the picture on the left-hand side, what you see is an iron ore picture I took around 2008, between 2008 and 2009. What you can see from a distance, there's a change in color. Is because there are two different types of alterations in that mine. So that's a geological interpretation right there. It can be simple. On the right-hand side, that image that you see, this is structurally cut many different domains in here. Domain basically means a three-dimensional space with some characteristics in there, and that makes the geology model in that deposit. Here's an example I got from internet. It just shows that the grade model sometimes we can have interpretation based on how much gold or silver or iron content in the rock. And those are basically called grade models, right? It's called grade model because your interpretation is basically based on the grade distribution. For an example, like gold ounce per ton, or copper in percent. It's called grade model. Okay. In some cases, in the resource modeling, you can have grade model that works fantastic. In some deposits, not. You need to be very careful actually when and where you're applying certain concepts in here. Now, what are the best practices in the geology model? And I would encourage you guys to take a screenshot of the slide, or have a take a note. So first point, differentiate the geological controls of mineralization versus other. That means, like in this yellow red stuff I'm showing you, the red stuff are in this diagram in here. Let me see if I can use a pointer. In this diagram in here, you can see the yellow stuff are basically extrapolation. Actual drill hole data intercepted this red stuff in here. This is a gold deposit. I believe it's in a southwest corner of Nevada somewhere. And that's one thing. You must know what controls the geology, okay, and interpret it, and don't become too actually vague in interpreting on the corners of the property. Avoid unnecessary fine tuning. Again, using the similar type of diagram. If you have way too many triangles, it would be very difficult for you to handle, whereas it's adding no value. And avoiding extrapolate too much. In this diagram in here, what you see here are two intercepts of a large iron ore deposit. And here is the 200 meters. The iron ore goes up to like half a kilometer, maybe in one case 1 kilometer deep from the surface. The surface is pretty flat. In this case, you see these guys actually extrapolated the interpretations to go that way. That's one of the reasons why this brown line is called a optimum pit line. So this surface as well, if you have mineralization here, I'm gonna take that material, but it's not supported by the data. So you must have a good geological model that you can defend. Let's move on to EDA. Like I said in the beginning, EDA really means understanding them and modeling the statistical structure of the data that leads to the selecting parameters for the gradation. First of all, we need to understand the statistical structure in the data. What I mean by that, let's say you have a sample set, and you have a histogram of it, of let's say copper percent. Then that histogram represents the statistical structure of copper in that particular data set. I hope it makes sense. Then another example can be, now you have a statistical table, and that describes the commodity that you are trying to mine. That can be such a statistical structure too. Mainly what I mean here by statistical structure is the diagrams, like histogram, cumulative frequency charts, and something similar to that. When you use the drill hole data analysis, the data can be many things. It can be asset data, that you take it, composite it, and then I can decide which composite is the best. Here's the way I do the work. Sometimes I look at the drill hole data, and you see some of the intercepts are really different. There are too many of them. In this particular image that you're seeing, the 4-meter asset length, the ton of them, so more than 60% of the data has a 4-meter asset length, right? So when you do the compositing, make sure that You understand how this assay length was chosen and who did it and what the purpose of it. From my experience, I can tell you sometimes when you cut through a waste rock portion, let's say dike or something that intercepting your nickel deposit, that you can have a bigger intercept, right? Because there is no financial value in there. That I've seen people doing it. In other cases, I've seen in that particular example, you can have the maintain the assay length. For an example, it can be let's say 2 meters, and if you still log the dike the same ways as the ore, maintaining the same assay length. Now, there are many ways you can see whether assay length has any trouble or not. This is one of the ways, very simple ways. If you come to my classes, my teaching, you will see that I use very simple languages to explain certain things. Many times I would say, take a note that your Excel can do a lot of good diagrams that helps you to make decisions. See, in this diagram, it's a gold deposit here, this is iron ore deposit here. What you see in this gold deposit case, there is a substantial amount of data that's actually at the 3 meter assay length. In the right hand side, the gold assay data, what I saw that 2, 3, and 4, and 5 meter length assays all mixed together. Make sure that you composite them to bring to one particular length. So why compositing is important? Because if you leave the assays the way it is because of differences in lengths, the larger length data may have a lower weight in your estimation compared to smaller intercepts in there. So we need to be very careful. These are different types of compositing that you can do. The most popular one is the round length one. The round length compositing is the most popular one. Just a second, what happened? Round length in here. Okay, that one is the most important one. Now, this is entirely from my experience in the industry. There are 3 different ways people decide which composite length they're going to use. First one is guided by the bench height. For example, if you have a mine bench going like this, and you can say, and your drill hole really goes like, like that, you may come back say, I'm going to composite it like this, matching the mine length, so mine bench height. That means these assay and this assay, they're not actually the same. They're not the same. They can be of different lengths. Okay. And in my experience, this is the best way to do. If you have let me go back a couple of slides, like this situation here, close your eyes, just simply take the 4 meters as the composite length. You will not doing anything wrong. Okay. And here I'm gonna jump to slightly to the geostatistics part. We talked about spatial statistics, okay, or classical statistics. When there is a space involved, like in this particular case, there are 40 different samples spread all over this area. If you have coordinates attached to that, then you can know the location. That will make a huge difference in your interpretation of the data. If you rearrange this data into like this, well-graded kind of box type of thing, your classical statistics will give the exactly same values. However, just a second, that because they're spread differently, their statistics can be different. That's called geostatistics. Geostatistics is based on a relationship between samples of the same variable at 2 different locations. Okay, this is the fundamental diagram of the 2-point geostatistics, or the geostatistics that we see being applied most popularly, like kriging, ordinary kriging, lognomic kriging, all that is based on this relationship. Okay. Why geostatistics is important? is because we know the data may not be homogeneous. That means if you have a domain here and another domain is here, they may not have the same type of data. And if they, if you want to combine them and assume that that you can combine them because they come from rock types, you may see that they are heterogeneous data sets. Okay, their properties do change with space. Based on their locations. Okay, and when they're different, it's called heterogeneity. And with another powerful contribution of geostatistical mining is it can take two variables and basically it can establish the bilateral relationships and use that to evaluate the variable that has been undersampled. I'll give an example. Let's say you have a gold deposit, but you have silver with it, and not all the silvers are sampled. Now, using bivariate relationship, sometimes we call it co-kriging, co-simulation, what do you call it? Sequential Gaussian indicator kriging. Sometimes we use co-kriging also. So co means two variables at the same time. You can use simulation, you can use estimation. Sometimes they just use the word called co. That means two variables involved in it. I don't expect you to remember this. Just to know what the definition of variogram. Variogram is nothing but a curve that represents the degree of continuity in the mineralization. You may remember the variogram looks like this, right? Another variogram may look like that. Okay, so but these whichever model fits your data, that remember that represents the degree of continuity of mineralization. That means if a directional variogram, you can use the directional variogram. Say, well, let's say not 45-degree east direction, we have a larger range of the variogram. This is called range of the variogram, where the variogram really flattens, and larger range. That means along that direction, we can have the degree of continuity much higher compared to other ones. I don't want to, I don't expect you to understand this. Now, this is an important slide. What are the admissible variables? That means authorized variable. That means these are the variables that are coded in the software that you use. Most popular one is spherical. Sometimes it goes to also, some deposits are good for exponential or Gaussian models. Okay, this is a typical model called Holyfield model when you have the data varies from top to bottom because of the lithological changes. It's like looking at the drill hole data, and you have a different rock types as you move from top to bottom. Isotropic means the variogram behaves the same way in all directions. Variogram is a model that is used in the estimation called kriging or co-kriging or indicator kriging. All these kriging terms that depend on the variogram. So if the variogram says, okay, I have an isotropic case, the kriging estimation will give you the results that will actually will look like, in different directions they behave the same way. But as we know, most of our data is actually anisotropic. When you have anisotropic case, that means the property changes with the direction. Just to know that, that's how it is. And to measure the anisotropy, I strongly advise, please do a variogram map that may look like this. This is from the software called Isatis. You can have the similar variogram maps or compare variogram maps using Vulkan, Datamine, software, and any of those software tools with a geostatistics module with you. What we do in the model is basically we estimate the value where we don't have an estimate. For example, in this is, let's say there's some of the blocks we don't have the drill holes going through them or close to them. Now we are going to estimate. That means we're going to do estimate a value that is very close to the reality. That's why hoping the product and planning. Different types of gradation techniques. Now, kriging is a geostatistical technique, which is also a deterministic geostatistical technique. Okay, and these are non-geostatistical techniques. They are listed in here. So I classify the interpolations in two different ways. One is geostatistical or geostatistical or statistical or non-geostatistical. It can be also the polygonal technique is the simplest one. It's our lithium coal, you may use the power, in the power, the estimation also change. Just something actually you should know. As you is called input power 2I distance of separation and square. This is called input square. When you don't have that, you have. Oops, sorry. When you have, let's say you increase the power to 3, and you move on, getting more powers there, maybe 4. Maybe actually you have another power called power 5. When you do that, as you increase the power, the weight on the samples in the estimation will be close to polygonal technique. They'll move away from the kriging that you're doing. This is the most common interpolation technique called ordinary kriging, most common in mining. The environmental guys also doing lots of kriging. You will see kriging application also, because there are a lot of smoothing got to do in the interpolation that's used also kriging. Just to know, the ordinary kriging is the most popular and common type of deposit. Common type of technique. Just to show you that when you're using a software to behind the software in some data goes there. More time computer takes the sample. If you use too many samples, that will lead to a word is called smoothing. Okay, so the value on the block can be close to the average of the samples, and it would lead to a non-trustworthy type of estimation. We talked about it. Just remember, to be able to use kriging, you must understand geology. That's, I think, mostly this slide is talking about. And while you should be using, make sure that your data is correct. The data is ready for using kriging. The underlying assumptions of second-order stationarity are met. So that's a test to see whether your data is good for estimation or not. Here's an example from Margaret Armstrong's book. It's a really good book. I'm assuming that you may find this book in your library. Have a look. Here, Dr. Armstrong says, well, if you compare using the same data set, if you compare the kriged estimate versus the polygonal technique, your kriged estimate is closer to the true grade. You know what true grade means? True grade means most of the time, it's the grade that you get in the drill hole data, and when you're mining, you're also achieving that data. Most of the time, this is the blast hole data. Blast hole data. That's a true grade, and that's actually from their book. Ordinary kriging is simple. There can be various different variants of the kriging. Like I said, you can have co-kriging for 2 variables. Indicator kriging is a variety of kriging where you can use use that kind of kriging for categorical data. And there are many other techniques too, like these are non-linear techniques too. Drawbacks of the kriging is a linear technique. Remember, it cannot give you the probability answer. So you can't say that my estimation is at 90% confidence interval, my estimation has this much truth in it. You just can't say it. And it can have a negative weights. There's a special case. If you join my classes, you will see that I discuss a lot about where possibly there is a negative weight you can have. It again, at the end of the day, the estimation quality doesn't always depend on how many samples you took, what kind of variable you used. Rather, it depends on all of that. Starting with geology model, how good is your geology model? What are the source parameters you're using for the estimation? So it depends on all of that, not just one region or one variable. That is where the estimation actually dependent on those. And one of the examples, this is from a project I did around 2006 or 7, something around that. Just simply tweaking the search ellipse. This is what they used before. I said, no, let's actually just match it with the geology without doing much of the biography in here. What we see that, I'm supposed to give you a quiz here, but don't worry about it. So basically, it says that, the search ellipse that is actually kind of aligned here with the geology is probably a better search ellipse for this deposit. Now, if you have a grade estimation, it has lots of grade, let's say here's the histogram of the assay data. You have a lot of high grade stuff in here. There are some high grade stuff in here, but they may be very little. If you take care of the high grade value, that means make sure that there's not much smearing going on. That means these high grade stuff, high grade values are not actually impacting all the mid grade and low grade blocks. So when that is not happening, when you take care of it, in this particular case, I have a zinc deposit. You see this grade tonnage curve is the resultant of and the resultant of taking care of the high grade stuff, and that is substantially different from the green line. It's about 14 to 15% in terms of tonnage in this particular deposit. So you need to be very, very careful. Actually, all these things that you're using in the estimation. How actually you know the grade estimation is good? You check them visually, do some statistical validation, use grade tonnage curve, swath plots, all those you got to do at least 4 different types. I will not be surprised if you come and say, hey, Dr. Samal, we saw an NI 4311 report. They just said we did visual validation and it's all correct. So I'm not saying that everyone does it that way, but this is ideally you do 4 different types of checks. That gives you a better understanding. Visual validation is this one, right? For example, the drill hole data here, you can see the lines type of things. And when you have like this drill hole intercept, when I have estimation done, you see you can match the colors, right? And see if they are good match or not. Can use statistical table to check it, and statistical plots. In particular case, in this one, you can see the blue line here is the data. In the diagram, you have the blue lines. They are the data, input data, and the block model can be the red or black. So you can see the black lines in here. They are, this one and this one, they're in the nearest neighbor model. Okay, there's a reason behind why they're doing that. When you have this is for a silver grade model. When you have the red lines in here in this histogram, that is representing a version of the silver interception here. You can also check comparing the lines in here, right? Composite versus, block model. And there's another way of doing the plots. Swath plot is nothing but in the space, like in this example, I think it's going from west to east. You can take you can compare the model, which is blue line with the blast hole data. Okay, you can also load here for comparison purpose. You can also use the input data, which is actually it's just is a expression data. You can actually use that. You can use 2-3 variables and coming from one set of data and compare them as you go from west to east. Are they similar? Here's the point. If you see the block model is exactly same as the input data, that is wrong because there is no software written yet that can give you exactly same software. They have to change. Okay, and you can also look at the gradient curve. How do I take different models from the same deposit, compare them? You'll see, well, one gradient curve is better than the other one. Look at this red line on the right-hand side diagram in there. What you see, this is a nearest neighbor model. This red line in here and this red line in here. They seem to give an idea that, well, this deposit may have a lot of copper in this deposit. However, if your copper actually, at this cutoff grade, what you're looking at, this model gives an impression that you may have a lot. Actually, that's not true. Once we change the nearest, from inverse transfer to picking, what we see that, these lines are actually, kind of overlapping here. That means, when you have that kind of scenario, you'll say that, well, even if I change my interpolation techniques, the grade and tonnage lines look similar. That means my parameters are good. Okay, and sometimes you can use the Harco diagram. Let me skip it for the time. Why it's so important? It's important because you see in the beginning we talked about going from preliminary economic assessment or the what do you call it scoping study to going to PFS and FS. As you move from left to right in the diagram, what you see, here is actually a preliminary economic assessment type of GERD model, the geology model. After 10 years of work, they came up with this diagram in here. This is a copper deposit in Brazil. And this one is a feasibility level work. Very, very robust. And it is robust and very reliable geological interpretation here. Why all this important? It's important because every mining needs financing. Okay, and each project requires the technical expertise in the various disciplines. You can be geology, mining, process engineer, economics, hydrogeology, amount geology, everyone. So the investors say, tell you what, we need transparent reports. It has the information that we need in there, the materiality, and it should be written by the competent persons. That's actually what we call NI 4311 report, a job style report. Those are what we do, right? It's written by competent person. I am a CP, or in different company, in a different country, they may say I am a QP or qualified person. And they mean exactly the same thing. It's just different countries they use is different words, and they should be the responsible for making the reports in here. Okay. Now we're talking about reports. When you estimate the values, when you write a report, it's a big skill to have it, and it takes actually tens of years to perfect it. It relies on the competency. That means there has to be a competent person in it. This is a slide kind of nicely defines what a competent person is. First of thing, a mineral industry professional. He works in the industry. It can be geologist, a mining engineer, a process engineer, something like that. Member of a professional organization that is recognized by CRISCO. Okay, in the United States it's SME. Let's say I'll show you the whole list of the countries, that 15 different countries. Every country has a recognized organization. Like in Australia, is the AusIMM or AGI, Australia Geological Institute, right? Those can be the as a QP you are actually attached to one of those. The minimum 5 years of relevant experience. What relevant means here, in the context of writing a report. If a report says you have a resource model in a porphyry copper deposit, you should have 5 years experience in that kind of style of mineralization. Okay, For example, if you spend all of your time in a sedimentary copper deposit, you never work on a granitic intrusive type of system, then you may not be qualified to write a report, because you may not have 5 years of relevant experience in there. This is a key takeaway from this slide. A competent person faces their peers and demonstrates the competence in the commodity type of deposit and reporting activity they're undertaking. So that's kind of test. When I sign my name as a competent person, I say, well, the work that I'm certifying to be correct, can I face my peers defending my work, right? That's kind of a real test. I already talked about relevant experience, in the geologist, example. Here is this table shows that in different parts of the world, how competent persons' minimum qualifications, remember these are minimum qualifications, vary. Most of the countries, they require years of experience, 5 years, but some countries, Colombia, Turkey, India, Brazil, and Chile, they require 10 years of experience, out of which everyone says you have to 5 years of relevant experience, except Turkey. Turkey is 7 years. You will see that all the countries gradually going to change to 7 years. The two countries, they say you have to have position of responsibility. Position of responsibility is not same as your designation, like general manager or manager, senior. It has nothing to do with that. Rather, it says you are in a responsible position where you could make actually your own judgment, and that is valid. Okay, that's how all the competent person system worldwide are comparable and they're similar. What competent person does is, of course, writes a report and validates it. It also exercises judgment in providing external information. That means if one of you is a financing entity and you are depending on the true trustworthiness of my work, then I got to defend my work, how I made some judgments in that, coming up to a resource model and making some decisions in there. And you do uphold the principles of transparency, materiality, and competency. Never give up anything, any of these three. It takes a balance and reasonable investment decisions. So a competent person plays a huge role in merger and acquisition and investment decisions. And remember, if a competent person doesn't do the work properly, the disciplinary action may be taken against competent persons. In my case, I in my business card, say, well, this is a company I work for. Here are my competent person designation, CPG, and a registered member of SME. And here are my contact details. So anyone actually looking at it, so you should know that I have this type of projects I have done in my life, and also this is the types of an area of practice. These are area of practice. Here are the type of projects I have done. So people know who I am and what I do. And everyone, this is just my way of I handle it. Basically being at the 100% transparent there. So as we conclude this presentation, I would say a competent person report becomes the basis of potential financial decisions. It's a responsibility of the competent person. So becoming a CP is not necessarily just, it is a big thing because it has got the responsibility. It's not always just the designation, hey, you are an RM SME, it's a big thing. Yes, it is a big thing because we take the responsibility. You will see in a few days, I think next week onwards, you will see a US SK 1300 report, an NI 4311 report. Me and my team worked on, those reports will be online. They have been submitted like as of Monday. You'll see that we take the responsibility in that particular example that the numbers that we reported in this report are reliable, because some people are looking at the report and making decisions on those things. I think that's all I have. I'm pretty close to 1 hour. Stalin, is this good?
Yeah, really appreciate Dr. Samal.
Okay,
That
then.
was a really
I'm
interesting
going
and
to
good presentation.
thank you a lot for hosting me. I'm going to stop sharing and I'll take some questions.
Yeah, there are some questions in the chat. I can read it for you.
Okay.
So Marco asks, good evening. What are the main challenges in building an accurate resource model?
Main challenges. There are many of them, but main challenges are actually the knowledge base that you need. Okay, someone going, for example, if you're a graduate student, you're going back to the industry, you got to actually work at least 10, 15 years to be able to do a good resource estimation. And the other thing is, by accuracy, I know that you mean that how to predicting, you can mine it, right? Your prediction, your is reliable prediction. If you keep that, actually, I come back to the same thing, actually, how much knowledge you have in the model, and actually, to some extent, software, and one of the big things actually at the quality of the data. So there are three things. One is your competency. Second is the quality of the data. And the third thing actually related to competency is your software tool that you're using. Remember, I must qualify what I said. If you use for example, use a micromine software to create a resource model for the exactly same data, same model, a geology model. If you use SORPAC to create a resource model, this will be very, very similar, like within 1%. If they're different, that means there is a problem somewhere. Go ahead, Stalin.
Okay, thank you, Dr. Samal. Another question. What are the main sources of error in a geostatistical model?
Data quality and parameters. Parameters used in the estimation technique and data quality. Don't blame the software. Please don't. Okay, softwares are only tools. It depends how well you are using it. Parameters. People always talk about data quality. Data quality doesn't necessarily limit it to drill data. Data quality can mean also the topography data is not correct. For example, your density data may not be reliable. Those kind of things too.
Okay, thank you. Another question. Thank you for your lecture, Dr. Samal. I would like to ask, what methods can be used to validate a resource model?
So four different types of, like if you go back to what I said, you should use a first look at it, cut the cross sections and look at it. Second, statistical comparison, compare the input data with output is here, the resource model. And the third thing is visual, actually swath plot or something special. Because statistical techniques, like the statistical tables can be, spatial. It doesn't have space included in it. Like comparing mean, mode, median, standard deviations. Rather, use that along with swath plots. Okay. And also the fourth item is look at the Gretton's curve. I stress a lot on those things, Gretton's curve. Okay. And there are more details about statistical parameters. I strongly encourage you download up some of these NI41 reports. If you want to read my report, you are welcome to do that. Google it. You'll find the link and, look at it. See what are the methods used. Go ahead, please.
Okay,
Thanks. It's a good question.
I'm interested in this question because I'm also working with this. It says,
Mhm.
Milton says, what are the advantages of using artificial intelligence over traditional geostatistical methods?
Well, I am very much aware of the AI techniques being used, but I don't use it properly because it has not been matured yet. They is just at an experimental stage right now. My answer is I don't know really. When you're creating AI, remember AI is based on is dynamic statistical models of various things. It can be actually statistics of the asset data, statistics of the geology model, and there's a lot of probabilistic answers based on which AI results come on. One time maybe we'll get some sort of AI technique that includes the geostatistics, but we're at the experimental stage right now.
Okay. Marcus also has a related question. He says, how difficult is the implementation
Mm.
of artificial intelligence models in resource modeling?
I really don't know. There's only one company that's trying it. I haven't seen a successful model. There again, they're only experimenting, trying independent projects. So,
Okay, okay, thank you.
very good question, Stalin. A really enthusiastic crowd.
Okay, I
Thank you
have
for that.
I will share my screen because I have a final message I want to share.
Sure.
Window.
Oh, thank
Okay.
you. I appreciate that.
Okay,
Sure.
Dr. Samal, give me a moment. On behalf of our SEG chapter, we sincerely thank you for sharing your expertise with us today. We truly appreciate your time in contributing to our academic formation. And as a token of our gratitude, we would like to present this certificate of appreciation, which reflects our deep respect for your contribution. Once again, thank you for being with us today, and we look forward to staying in touch and hope to welcome you again in the future. Thank you also to all the attendants
Yeah.
for your questions.
Thank you, Stalin, and I really appreciate that too. Please stay in touch, okay?
Okay, thank you,
Okay,
Dr.
bye
Samal,
now.
and see you next time. Bye.